Okay, so hi everyone. Welcome to the session again. And today we'll be continuing our webinar on CCNA, the CCNA Accelerator. So in the last session, we discussed some concepts related to the spanning tree protocol, how it works, and what is the manual working of it. So we looked into the internals of STP. Now, the next thing that we'll be moving on to the IP subnetting, the classful IPv4 networks, analyzing the subnet mask, the IPv4 addresses and static routes, understanding OSPF concepts, right? So let's start with the subnetting part, right? So what is subnetting, guys? How will you define subnetting? When I'm talking about an IP subnet, so when we are talking about a subnet, right? So it is simply a subset of class A, B, or C network, right? And word subnet is a shortened version of subdivided network, right? Let's say one subnet of class B, 172.16.0.0, right? This one could be the set of all IP address that begins with 172.16.1 and would include 172.16.1.0, 1.1, 1.2, and so on, right? Up till 255, right? Then another subnet of the same class can be 172.16.2.0. It will start from 2, right? That is another subnet, right? So here we can see 172.16.1 is the network, right, which is coming to a router. Then 172.16.3, 172.16.2, 16.4, 16.5, right? So these are different subnets. Now, when I'm saying subnetting, right? So how we do it and why we do it, right? Now, when we are doing subnetting, we are dividing the network into smaller parts that we know, right? Now, what we have to find out that which hosts are in which subnet. So every device that connects to an IP network, it needs to have an IP address. Now, these devices they include computers used by end users, servers, mobile phones, laptops, IP phones, tablets, networking devices like routers, switches, and firewalls, right? So, any device that uses IP to send and receive packets needs an IP address. Now, the IP address must be assigned according to some basic rules and for good reasons, right? So to make routing work efficiently, IP address rules group addresses into groups called subnet, right? And there are two rules, right? The first one is the addresses in the same subnet, they are not separated by a router, right? And addresses in the different subnet are separated by at least one router. Now we have to find out how many hosts can be there in one subnet, right? So let's understand this thing. When the internet was young and IP addressing was new, so what we used to do, we used to break IP addresses into classes, right? Now, how many classes are there in total? Five classes are there, out of which class A, B, and C are usable, right? Only these classes are used to give IP addresses to the users. Perfect. Now, when I say that we used to break IP addresses into classes, so what we used to do, right? Let's understand it here, the subnetting part, right? So we have different classes, right? Class A, class B, class C, class D, and class E, right? Now, class A is having IP addresses ranging from 1 to 126. Now, that means 1.0.0.0 till 126.255.255.255, right? Same like that, class B is having IP addresses from 128.0.0.0 till 128 till 191.255.255.255. Yes. Now class C 192.0.0.0 till where 223.255.255.255, right? Class D is also there. Now class D is used for multicasting, right? Now class D IP addresses are from 224.0.0.0 224 till 239, right? Dot 255 dot 255 dot 255. Then there is class E, right? Class E is having IP addresses from 240 till 255 dot 255 dot 255 dot 255. Yes. When I'm talking about these classes, every class it has a subnet mask. Yes. Now, what is subnet mask? We know what is subnet, small part of a network. What is a subnet mask? Now, subnet mask does what? Subnet mask separates the host bits to the network bits. So, subnet mask is the way by which we can define how many hosts can be there in this subnet, right? So, by default, when we were doing IP addressing, right? So, we were doing classful IP addressing, right? Now, in this, the subnet mask was 255.0.0.0. For class B, it was 255.255.0.0, right? Then for class C, it was 255.255.255.0, right? This is the subnet mask, right? So the place where 255 is written, these are network bits, and the place where 0 is written, those are host bits. Clear? Yes. Now I'll give you guys a task as well after I tell you how to do it. Right. Now the thing is, let's say we have a subnet mask of class C. I pick up the subnet of class C, right? So the subnet mask of class C is 255.255.255.0, right? Now any IP address, when I'm talking about IP address, every IP address, it is in, it is a size, like it's of two types, right? Version 4 and IP version 6, right? So right now we are talking about IP version 4. So what is the size of IP version 4? Now why 32 bits? A IP address looks like this. Let's say I'm taking one IP address 192.168.175.147, right? This is the IP address. So this place is called an octet, right? Octet, oct means 8. So every octet is of 8 bits, and there are 4 octets, right? 1, 2, 3, and 4, right? So 8 plus 8 plus 8 plus 8, that makes 32. So that's why the size of IP version 4 is 32 bits. Now, behind these octets, like this is a class B octet, right? IP address. So now I've taken subnet mask of class C, right? 4 octets are there in the subnet mask as well, right? So we will be doing what? We'll be expanding this subnet mask, right? So as I said, oct means 8. So what it will be having? It will be having every octet 8 bits, right? So let's start with this. 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Now, how we start the numbering? We start the numbering from 2 raised to the power 0. So here it will be 2 raised to the power 0, 2 raised to the power 1, right? 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, 2 raised to the power 5, 2 to the power 6, and 2 to the power 7. So in all the octets, this will go on, right? From 2 raised to the power 0 till 2 raised to the power 7, right? Now let's write the normal numbers. So 2 raised to the power 0 is 1, 2 raised to the power 1, 2, 2 square 4, 2 cube 8, 2 raised to the power 4 16, 2 raised to the power 5 32, right? Then 2 raised to the power 6 64, and 2 raised to the power 7 128, right? Same here, 1, 2, 4, 8, 16, 32, 64, 128, 1, 2, 4, 8, 16, 32, 64, 128. These are all the octets of your subnet. We never do the calculation on IP addresses. We always do the calculation on subnets, right? Right now, we have 255.255.255. Now, here you should remember that 0 means off and 1 means on, right? So, 1, 1, 1, 1, 1, 1, 1. If all the bits in an octet are on, so all the on bits you have to add up whatever number is written below it, right? So here it's written 128. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, because all the bits are on, right? So a total of all of them becomes 255. That's why here it is written 255, right? Now, by looking at any subnet mask, you can find out that what is written, right? So the second octet, we can see the second octet also has 255 written. So that means all the bits are on here as well. right? Then in the third octet also 255 is written. That means all the octets are on here, right? And in the last octet you can see .0 is written. So all the bits are 0. That's why the output is 0, right? So all these on bits, the ones that you can see, these are your network bits. All the zeros are your host bits. Now, if you want to find out that in any subnet of class C, how many IP addresses we can put or how many hosts we can add, right? So you just have to follow a formula, right? Now the formula is 2 raised to the power n minus 2, right? Where n equals to number of zeros, right? So how many zeros are there in this subnet? 1, 2, 3, 4, 5, 6, 7, 8. So 8 zeros. So 2 raised to the power 8 minus 2. So 2 raised to the power 8 is 256 minus 2, right? Now 256 minus 2, 254. So in class C subnet, you can have 254 hosts. You are working into networking, and it is asked from you that you have to purchase 30 new IP addresses, right? So what you saw all the classes, right? Then in classes you see that the least number of zeros are in class C. So you will pick up an IP address of class C, right? So let's say you picked up an IP address as 192.11.1.0. From here it will start, right? So you all the calculation was done, and after this calculation, like the default subnet mask for class C is 255.255.255.0, right? That means we can see the first three octets are on. So we put 111 111 11 in every octet in the first three octets, right? Now in the last octet, all are zeros, right? So we found that we got 254 IP addresses, right? But I needed only 30. Now you needed 30, you are getting 254. That means 224 IP addresses were getting wasted. So that was a lot of wastage of IP addresses. So we have to minimize the wastage, right? So what we did, we moved to something which is known as classless IP addressing. Now, classless IP addressing, what was the change? The change was like all the things were same, right? All these things were same. But now this time, this subnet mask that we talked about, this subnet mask was dynamic. So let's see this classless. Now, five classes, class A, class B, class C, class D, and class A. Right. Now, class A 1 to 126. Right. Class B 128 to 191. Right. Class C 192 till 223. Then class D 224 till 239. Right. And class E 240 till 255. Right. Now we know the subnet mask 255.0.0.0 for class A, then 255.255.0.0 for class B, and 255.255.255.0 for class C. Now there came one new thing which was known as CIDR. Now CIDR stands for classless inter-domain routing. Right. Now, in this classless interdomain routing, it is a notation, right? Now, in this subnet or in this notation, what we do, we write the subnet mask in slash notation, right? So, check out this, right? This is the subnet mask in front of you. Now, in this subnet, whole subnet mask, can you tell me how many on bits are there? 8. By looking at 255, we know all the bits that are on are 8. So instead of writing this 255.0.0.0, we'll write slash 8. Right? Same like that, in the second one, two octets have 255 written. So one octet has 8 bits, right? That means here we'll write slash 16. Right? Then the third one, right? It has first three octets on. So slash 24 because 8 plus 8 plus 8 is 24. So this is the notation. Now the thing is this CIDR, it is dynamic. That means before we were not able to change the subnet mask of an IP address, right? But now we have the ability to do this. So we'll see how we can do that. Now let's say again we have a need of 30 IP addresses. Yes. Now we are having the need of 30 IP addresses, so we'll pick up class C. In class C, we have 255.255.255.0, right? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. Right. Now let's do the numbering. 1, 2, 4, 8, 32, 64, 128. Right. Same here. 1, 2, 4, 8, 16, 32, 64, 128. Then here also 1, 2, 4, 8, 16, 32, 64, 128, 8, 16, 32, 64 and 128, right? Now we know that all the subnets, all the octets, first three octets, they have all the bits on, right? Because 255 is written, right? And if you add all the on bits in one octet, in any octet, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, so it becomes 255. That's why we have put all the bits on, right? Same here in the third octet also it is written 255. So what I will do, I'll put the third octet bits as on also, right? Now the next thing is that if let's say I want 30 IP addresses, right? So in class full IP addressing we were getting how many? 254 IP addresses we were getting. We need 30 only, right? So what we do? In the last octet, all of them, like all the bits, they were zeros. Now what we have to do, we have to find out a number which is near to the number of IPs we need. We need 30 IPs and a number near to 30 I got is 32 here, right? So till 32 I will put the bits on 111 and I'll put others as 0, right? So I have what changes I have made to the subnet mask. I put three more bits as 1, right? Now, if you apply the formula again, 2 raised to the power n minus 2, right? So this time n is 1, 2, 3, 4, 5. 2 raised to the power 5 minus 2, which becomes 32 minus 2 equals to 30. So you need 30 IP addresses, you got 30 IP addresses, right? So it was, we saved the IP addresses, right? Now why we made this minus 2? Let me make you understand that. Now the IP address that we are picking up, it's 192.168.1.0, right? Like this, let's say, right? This is our IP address. So the very first IP address, 192.168.1.0, right? Then the second one will be 192.168.1.1, right? And it will go till 192.168.1.31, right? Here it will be 192.168.1.30, right? So the first IP address is known as network ID, right? Now by this it is defined in which network you are sitting in, right? And the last IP address, this one, 31, this is known as broadcast ID. That means if any device in the network is sending data to this IP address, that data will be received by everyone in the network, right? That is network ID and broadcast ID. So that's why from this in this formula we have written minus 2. So we removed the dot 0 and the dot 31, the broadcast ID. And these are the usable IPs which you can provide to the devices. So this is how you do the subnetting, right? Now the thing is that when we talked about the IP and IP addresses, right? So we used IP version 4. Yes. Now after using IP version 4, what happened? We ran out of IP addresses. right? Now, why we ran out of IP addresses? Eh, Like the subnetting you are doing, and you are finding out how many devices we can add, how many hosts we can add. The thing is, we have in total IP version 4 was giving 4.3 billion IP addresses, out of which 3.4 billion IP addresses were usable. So now think of it, every person, the population of the world is 8 billion, right? Let's make it half, right? Let's say that only uh, half of the population is using the devices. Now, nowadays, every person has minimum two devices, right? Like a laptop and a mobile phone, or two mobile phones, or laptop or two mobile phones, two laptops, two mobile phones. Like different people live for different work. Like a personal laptop is there, and a official laptop is also there. So many people, they are having multiple devices, right? So 4 billion people are using even a single device. Even then, we were not able to give the IP address to all the devices. Now we have smartwatches as well, smart devices as well, which connect over internet protocol, right? So the thing is, we were not having IP addresses. We ran out of IP addresses. And out of that, the thing is, we have we moved to IP version 6, right? Now, what is the size of IP version 6? 128 bits. So it is 128 bits, right? Now, how many IP addresses it can give us? So it gives us a total of 340 undecillion IP addresses, right? Which means 340 trillion, trillion IP addresses. Yes, and that's a lot. Now even you don't have to think about the IP addresses getting wasted. Yep, perfect. Next thing, we have heard of private IP addresses. What are private IPs? So let's start talking in terms of public and private IP networks, right? So when we are talking about the internet, the original design of internet required that any company that connected to the internet had to use a registered public IP network. And to do that, the company would complete some paperwork describing the enterprise internetwork and the number of hosts existing, plus the plans for the growth. And after submitting the paperwork, the company will receive an assignment of either class A, B, or C network. Right now, the public IP networks and the administrative processes surrounding them ensure that all the companies that connect to the internet all use unique IP addresses. In particular, after a public IP network is assigned to a company, only that company should use the addresses in that network. And that guarantee of uniqueness means that internet routing can work well because there are no duplicate public IP addresses. Okay, if you see this image, right, company 1 has been assigned a public class A network 10.0.0, and company 2 has been assigned public class A network 2.0.0.0, right? Now, per the original intent for public addressing in the internet, after these public network Assignments have been made. No other companies can use addresses in class A networks 1.0.0.0 or 2.0.0.0, right? So this original address assignment process makes sure unique IP address across the entire planet, and the idea is much like the fact that your telephone number should be unique in the universe. Your postal mailing address should also be unique. Your email address should also be unique. So if someone calls you, your phone rings, but no one else's phone rings. Similarly, if company 1 is assigned class A network and the engineers in company 1 assign address 1.1.1.1 to a particular PC, that address should be unique in the universe. A packet sent through the internet to destination 1.1.1 should only arrive at this one PC inside company 1 instead of being delivered to some other host, right? That was the one way. Now, next, let's talk about private, right? The public IP networks, public and private, right? So now, when we are talking about private IP networks, when you are using NAT, network address translation, and almost every organizations that connects to the internet, it uses NAT, right? Network address translation. That company can simply pick one or more private IP addresses or networks from the list of reserved private IP network numbers, right? Now, from the perspective of making IPv4 work for the entire world, private IP networks have helped to preserve and extend IPv4, and its use in every enterprise and throughout the internet was there. So, in a particular private network, it was like improved worldwide by doing what? By avoiding using another organization's public address range for private networks, right? Avoiding or delaying the IPv4 address exhaustion, reducing the internet routers routing table, right? So these are the ways by which we have improved the IP version 4 networks. Perfect. Now, when we are talking about private IP address classes, right? So in private IP addresses, how many classes are there? There are three classes, right? Class A, class B, and class C, right? What class A is? What IP addresses will be there in class A? 10.0.0.0 till 10.255.255.255. Class B is having 172.16.0.0 till 172.31.255.255. Then in class C, the one that we use a lot, 192.168.0.0 till 192.168.255.255, right? So these are the private IP address classes. So we use private IPs just for communicating inside the network, right? Internally. Now, the next thing we learned about the IP addresses, the classes of IP addresses, but one thing is missing here, which is a range of 127. So it's class A is 1 to 126, class B is 128 to 191, but I have not written 127. What is 127? Loopback address localhost. Great. So 127 is known as loopback IP, right? So the whole range of uh, 127 is given to loopback IP. Right now, what does that mean? Loopback. That means this is the IP of your own device, your home address, which we call, right? So this loopback IP address is used in troubleshooting times when you are troubleshooting the network, when you are not able to access the internet sometimes, right? So the very first thing which is checked is loopback address, right? So if you are able to ping this address and you are getting a reply, right? That means your TCP/IP protocol stack is properly installed in your system. Now the thing is, uh, we discussed about VLANs, remember? Yes, everyone remembers VLANs. Now, when we discussed about VLANs, routing happens in VLANs also, right? Using IPv4. So how that happens? Now, when we are talking about VLAN, so almost all the enterprise the networks use VLANs. So to route IP packets in and out of those VLANs, some devices, either routers or layer 3 switches, need to have an IP address in each subnet and have a connected route to each of those subnets. Then the IP addresses on those routers or layer 3 switches can serve as a default gateway in those subnets. See, let me repeat. So to route the IP packets out of the VLANs to in and out of the VLANs, like routers or layer 3 switches, they need to have IP address in each subnet and they should have a connected path to each of those subnets. Then the IP address on those routers or layer 3 switches can serve as default gateways in those subnets. Now there are four categories of LAN routing, right? So user router, right? Let me write here, right? So user router with one router LAN interface and cable connected to the switch for every VLAN, typically which is not used, right? Then user router with a VLAN trunk connecting to a LAN switch, right? Which is also known as ROAS. ROAS means router on a stick, right? Now, other thing, use a layer 3 switch with switched virtual interfaces right? Then there is one more possibility, use a layer 3 switch with routed interfaces. Yep. So these are the four ways, right, that by which you can work with the routing of VLAN. Right, either use layer 3 switch or use two routers or connect the router to the VLAN's trunk. Okay, now we are going to discuss about the OSPF, right? So before that, we have to talk about the dynamic routing protocol features, right? What is dynamic routing protocol? Now, dynamic routing means, see, when we are talking about routing, so your data is going from one router to another router, right? Let's say you have this router right here, right? Now this is your router. Your router will send data to a next router. Yes. When it is sending the data from one router to another router, how this router knows, your home router knows where and to which router I'm sending the data. How it gets to know this thing? So there is a table inside every router which is known as IP routing table, right? Now that routing table keeps on updating and it has the hop of the next router, right? The whole internet is connected, right? So it has what? It has a path or it has the information about the next router that where to send the data according to your target, right? So there can be multiple routers, right? Now according to your target, maybe your router is sending data to router 2, right? You have router 1, right? There is R3, there is R4. So maybe your router is sending the data to router 2 or router 3 or maybe router 4 according to the target, right? So the information about these routers are saved inside IP routing table. When this routing table keeps on updating, right? So that is known as dynamic routing, right? In organization, what happens? We have specified a path. So in the routing table, we don't keep it dynamic, we keep it static so that it does not change, right? I have given an IP address that whenever any data arrives, you have to send it to this router only, nowhere else, right? That is static routing. Now, as I said, the routers they add their IP path or IP routes to their routing table using three methods, right? First, connected routes, right? Second, static routes, and third is routes learned by dynamic protocols, right? So before starting, it is important to define few related terms, right? About the terms routing protocol, routed protocol, routable protocol, right? So these are three different things. Now, concepts behind these terms are not that difficult, but because the terms are so similar and because many documents I have seen that they pay poor attention to when each of these terms is used, so they can be a bit confusing, right? So the first one is routing protocol. So routing protocol is what? A set of messages, rules, and algorithms which are used by router for the overall purpose of learning the routes, right? And this process includes the exchange and analysis of routing information. So each router chooses the best path to each subnet and finally places those best routes in its IP routing table. Like we have uh, RIP protocol, EIGRP, OSPF, BGP, right? Now, routed protocol, next thing is routed protocol, right? So, what is routed? Routed protocol and routable protocol, right? Now, both terms they refer to a protocol which defines a packet structure, logical addressing, and it allows routers to forward and route the packets, right? So routers they forward the packets defined by routed and routable protocol like IP version 4 and IP version 6, right? So even though routing protocols like OSPF are different from routed protocols like IP, they do work together very closely. And the routing process forwards IP packets. But if a router does not have any routes in its routing table, that match a packet destination address. So router discards the packet, right? Router needs routing protocols so that routers can learn all the possible routes and add them to the routing table so that the routing process can forward routing protocols such as IP, right? Now, what is like when I'm talking about routing protocol functions, right? So if we talk about routing protocol functions, Cisco iOS, the operating system in Cisco devices, that software supports several routing protocols and they perform the same general functions, right? Like learning the routing information about IP and subnet from neighbor routers, advertise routing information about IP subnets to neighboring routers, and then if more than one possible path exists to reach one subnet, pick the best route based on a metric, right? And if the network topology changes, right, let's say a link fails, so it reacts by advertising some routes have failed and pick a new currently best route, right? Now in this image, if you can see, right, router 1 here, this one makes a decision about the best route to reach the subnet connected off to router 2, right? So for that, router 1 does what? Router 1 advertises a route to the lower right subnet, right? 192.172.116.3.0/24 to both router 1 and router 3. After router 3 gets to know about the path to this router 2, router 3 advertises that to router 1, right? That this is the path. Now router 1 must make a decision about the two path it learned for reaching the subnet, right? With metric 1 from router 2 and one with metric 2 from router 3. So R1 router 1 will choose the lower metric route through router 2, right? Now the other routing protocol functions like convergence occurs when topology changes. So that is when either a router or any link fails or comes back up again, right? So when something changes, the best route available in the network can change. So what is convergence? We discussed about it. So convergence refers to the process by which all routers collectively realize something has changed and advertise the information about the changes to all the other routers. And all the routers then choose the currently best route for each subnet, right? So the ability to converge quickly without causing loops is one of the most important consideration when you are choosing IP protocol to use. right? Now, next thing, we have interior and exterior routing protocols, right? So the IP routing protocols, they fall into two major categories, right? IGP, interior gateway protocol, and exterior gateway protocol, right? IGP is a routing protocol that was designed and intended for use inside a single autonomous system. EGP is a protocol which was designed for use between different autonomous system, right? So there is a new term, autonomous system. Now, autonomous system is a network which is under the administrative control of a single organization, right? So let's say a network which is created and paid for by a single company is a single autonomous system. A network which is created by a single school system is probably a single autonomous system, right? Like large divisions of a state or national government, where government agencies might be able to build their own networks, right? That is also autonomous system. Each internet service provider is also typically a single different autonomous system. So some routing protocols, they work best inside single autonomous system by design. So these routing protocols are called IGPs, right? Routing protocols which are designed to exchange routes between routers and different autonomous systems, those are called EGPs, right? So nowadays one EGP is used only, which is border gateway protocol, BGP, right? Now as we started talking in terms of autonomous systems, so each autonomous system can be assigned a number, right, which is called ASN, right? Autonomous system number. Like public IP address, right? The Internet Assigned Numbers Authority, IANA. We all have heard about IANA, right? They controls the worldwide rights to assigning the ASNs, right? And it delegates that authority to other organization around the world, right? Typically to the same organization that assign the public IP addresses, right? Now, when we are talking about IGPs and comparing the IGPs, right? So organizations, they have multiple options when they are choosing an IGP for their enterprise network. But most companies today use either OSPF or EIGRP, right? Now, when we are talking about this thing, so what happens? The IGP routing protocol algorithm, if we talk about, so a routing protocol's underlying algorithm tells how the routing protocol performs its job, right? Now, routing protocol algorithm, it refers to the logic and the processes which are used by different routing protocols and to solve the problem of learning all the routes and choosing the best route to each subnet, right? And converging in reaction to changes in the network, right? So there are three main branches of routing protocol algorithm which exist for IGP routing protocols, right? First, distance vector, right? Then there is advanced distance vector, right? And then the last one is link state, right? So distance vector protocols were invented first, mainly in the early 1980s, I hope. Right. Now, routing information protocol was the first popularly used IP distance vector protocol, right? With the Cisco proprietary interior gateway routing protocol being introduced a little later, right? And by early 1990s, the distance vector protocol, somewhat slow convergence and potential for routing loops, drove the development of new alternative routing protocols that use new algorithms, right? So we call them link state protocols, right? So we have OSPF for that, open shortest path first, and IS, right? So integrated intermediate system to intermediate system, right? These solve the main issues. They also came with a price. They required extra CPU, memory on routers with more planning required for the network engineers, right? Now, around the same time, the introduction of OSPF, right, came, right? So Cisco, they also created EIGRP, right? EIGRP, Enhanced Interior Gateway Routing Protocol, which use some features of the earlier IGRP protocol, and it solved the same problems as did link state routing protocols did. But EIGRP, it required less planning when you are implementing it in the network. So as time went on, EIGRP was classified as a unique type of routing protocol, right? Though it is used more like distance vector features than link state, so it is more commonly classified as an advanced distance vector protocol, right? Now the thing is, when we are talking about this the protocols, so one main thing which arrives, metrics, right? Routing protocols, they choose the best path to reach a subnet by choosing the path with the lowest metric, right? For example, this RIP, routing information protocol, it uses a counter of number of routers between a router and a destination subnet, right? Here you, if you can see in this image, right? Now OSPF totals the cost associated with each interface in the end-to-end route with the cost based on the link bandwidth, right? So a brief comparison of the metric used by older RIP versus the metric used by OSPF. It shows some insight into why OSPF and EIGRP they surpassed RIP, right? So in this image, router B has two like paths, two possible path to the subnet 10.1.1.0 on the left side of the network. A shorter route over a very slow link like bandwidth 1544, so 1544 kbps is the path, or a longer route over a gigabit ethernet WAN link, right? So you can see bandwidth here is fast, right? So RIP uses what? As I said, RIP uses hop count. So the left side of the figure shows the results of RIP in this network, if you can see, right? Using hop count, router B learns of a one hop route directly to router A, right? Through B's interface, right? Now B also learns of a two hop route through router C, right? So through B, router B chooses the lower hop count route which happens to go over slow speed serial link. This one, right? Now, routing protocols, they can be compared based on many features. Uh, Now, the thing is, RIP, if we talk about, right? Is it classless? Yes. And does it sends mask in updates? Yes. Subnet mask it will send, right? Then algorithm, which it uses, it supports manual summarization. Yes. Right? Is it Cisco proprietary protocol? No. Right? Routing updates, they are sent to a multicast IP address. Yes. In RIP, it happens, right? Convergence, it is slow in RIP, right? At the same time, if I talk about OSPF, right? So is it classless? Yes. Will it send subnet mask in the updates? Yes, it will, right? Does it supports manual summarization? Yes. Is it Cisco's proprietary protocol? No, it's not, right? But does it sends routing updates to over multicast IP address? Yes. And what about the convergence in OSPF? Now, these are the algorithms, right, for IGP routing protocols, right? So, the distance vector algorithm, it is used by RIP, right? OSPF, it uses link state algorithm, right? Now, when we are talking about OSPF, right? Before that, you should know about administrative distance. What is administrative distance? Anyone who has heard about administrative distance before? Now, many companies and organizations, they use single routing protocol, right? And in some cases, a company needs to use multiple routing protocols as well. So let's say if two companies connect their networks so that they can exchange information, they need to exchange some routing information, right? If one company uses OSPF and others uses EIGRP on at least one router, so both OSPF and EIGRP must be used, right? Then that router can take routes which are learned by OSPF and advertise them to the EIGRP and vice versa, right? And that process is known as route redistribution. Now, depending on the network topology, the two routing protocols might learn routes to be to the same subnet. When a single routing protocol learns multiple routes to the same subnet, the metric tells it which route is best, right? Now, when two different routing protocols, they learn the routes to the same subnet, because each routing protocol metric is based on different information. So iOS, it cannot compare the metrics, right? For example, let's say OSPF, it might learn route to any other subnet with any subnet with let's say the subnet is 10.1.1.0, right? So OSPF, it learn the route from subnet to the subnet this with metric 101. EIGRP might learn a route to the same subnet with metric 2195416, right? But the EIGRP learned route might be better route or it might not be, right? So there is simply no basis for comparison between two metrics, right? So when iOS, it must choose between routes learned from using different routing protocols, iOS uses a concept called administrative distance, right? And it is a number that denotes how believable an entire routing protocol is on a single router. The lower the number, the better or more believable the routing protocol is, right? So let's say RIP, uh, it has 120, right? So by default, administrative distance for RIP is 120. OSPF uses 110, right? EIGRP by default 90, right? So when we are using OSPF and EIGRP, router will believe EIGRP route instead of OSPF route, right? The administrative distance values are configured on a single router and they are not exchanged with other routers, right? So these are the administrative distances written in the table. By default, these are the administrative distances. Perfect. Now, let's dive into OSPF. So, routing protocols, they basically exchange information. Why? So that routers can learn the routes. The routers learn information about subnets, routes to those subnets, and metric information about how good each route is compared to others. So the routing protocol can then choose the currently best route to each subnet, building the IP routing table, right? Now, link state as it is written, here you can see OSPF is a link state routing protocol used in computer networks to determine the best path for data to travel from its source to its destination, right? So OSPF takes a different approach to the particulars of what information they exchange and what the routers do with that information once it is learned, right? So OSPF does something which is known as link state advertisement, right? Now let's discuss about those things. So link state, as I said, OSPF is a link state routing protocol, right? So link state protocol, they build IP routes with a couple of major steps. First, routers together build a lot of information about the network, right? The routers, the links, the IP addresses, status information, and so on. Then the routers flood the information so that all the routers know the same information. At that point, each router can calculate routes to all subnets, but from each router's own perspective, right? So the routers which are using link state routing protocols need to collectively advertise practically every detail about the inter network to all the other routers. And at the end of the process of flooding the information to all the routers, every router in the internetwork has the same information about the internetwork, right? Now, flooding a lot of detailed information to every router sounds like it's a lot of work. And relative to distance vector routing protocol, it is, right? OSPF, the most popular link state IP routing protocol, it organizes topology information using link state advertisement and LSDB, link state database, right? Now, the thing is about topology information. Now, here you can see LSA, right? LSA written. So, each LSA is a data structure with some specific information about the network topology, right? And LSDB is what? LSDB is simply the collection of all the LSAs known to the router. So this is LSDB. Here you can see all the LSAs, right? Now in this process, we can see the flooding process. So router 8 is creating and flooding its router's LSA. The router LSA for our router 8 describes the router itself, including the existence of the subnet as seen on the as seen here. R8 sending the original LSA for itself and other routers flooding the LSA by forwarding it until every router has a copy. So the flooding process causes every router to learn the contents of the LSA while preventing the LSA from being flooded around in circles. So basically, before sending an LSA to yet another neighbor, router communicate asking, do you already have this LSA? And then sending the LSA to the next router only if the neighbor has not learnt about the LSA, right? Once flooded, routers do occasionally reflood each LSA. So router reflood and LSA when some information changes. They also reflood each LSA based on the LSA's separate aging timer, right? Which is by default 30 minutes. The next thing is applying Dijkstra SPF math to find the best route, right? You might have, if someone is from the mathematics background, you might have heard about the Dijkstra algorithm. It was having like very heavy calculations. The link state flooding process results in every router having an identical copy of the database, LSDB, right? Every router will be having a copy of the LSDB of another router, right, in the memory. But the flooding process alone does not cause a router to learn what routes to add to the IP routing table. Although incredibly detailed and useful, the information in the LSDB does not explicitly state each router's best route to reach a destination. So to build routes, the link state routers have to do some math, right? So this algorithm is known as Dijkstra's SPF algorithm, right? All the link state protocols they use this math algorithm, Dijkstra shortest path first algorithm, to process the database. So that algorithm analyzes the database and builds the route that the local router should add to the IP routing table, right? Routes that list a subnet number and a mask, an outgoing interface, and a next hop router's IP address, right? So here we can see the steps initialization, right? Start with the source router, setting its cost to 0. Check neighbors, calculate cost to directly connected neighbors, updating if a lower cost is found. Select next router, choose the neighbor with the lowest cost as the next router. Repeat and mark repeat the steps 2 and 3 until all routers are marked as processed. Shortest path tree. So there is a tree which shows the best path to all the routers from the source, and then populate each router's routing table with the best path from the shortest path tree, right? So there are three phases, right? So how these OSPF accomplish the work of exchanging the LSAs and calculating the routes by first by becoming OSPF neighbors, right? What do you mean by becoming OSPF neighbors? Becoming neighbors, a relationship between two routers that connect to the same data link, created so that the neighboring routers have a means to exchange their databases, then exchanging the databases. So the process of sending the LSA to neighbor so that all routers learn the same LSAs, right? Then adding the best route. So all the routers they learn from same LSA, right? As we discussed. Now the process of each router independently running the SPF, right, on their local copy of the database, calculating the best routes and adding those IPv4 route to the IPv4 routing table, right? So the main thing here is all the things that you learned about OSPF. OSPF neighbors concept have the most to do with how you will configure and troubleshoot OSPF in the router, right? You configure OSPF to cause routers to run OSPF and become neighbors with other routers. Once that happens, OSPF does the rest of the work to exchange the LSAs and calculate the routers in the background with no additional configuration required, right? So when we are talking about the neighbors, the OSPF neighbors, these are the routers that both use OSPF and both sit on the same data link. So two routers can become OSPF neighbors if they are connected to the same VLAN or same serial link or same Ethernet wide area network link, right? Now, two routers they need to do more than simply exist on the same link to become OSPF neighbors. They must send OSPF messages and agree to become the neighbors, right? So what they do, they send OSPF hello messages introducing themselves to the neighbor, assuming the two potential neighbors they have compatible OSPF parameters, right? Then these two things they form an OSPF neighbor relationship that would be displayed in the output of like if you run a command in the router, right? The command is show IP OSPF neighbor, right? If you run this command, you will get it in the output, right? Now, this neighbor relationship also lets the OSPF know when a neighbor might not be a good option for routing packet right now. Yes. Now, let's say these are the two routers, right, which are in front of us, right? So, let's imagine router 1 and router 2 they form a neighbor relationship and they learn LSAs and calculate the routes that send packets through the other router. Now, months later, the router 1 noticed that the neighbor relationship with router 2 has failed. That failed neighbor connection to router 2 makes router 1 react. So, router 1 will reflood the LSAs impacted by the failed link, and router 1 runs SPF to recalculate its own routes, right? So finally, the OSPF neighbor model, it allows the new routers to be dynamically discovered, right? And that means new routers can be added to the network without requiring every router to be reconfigured. Instead, OSPF routers, they listen for OSPF hello messages from new routers and react to those messages, right? Then they attempt to become neighbors and exchange the databases. So these were the things about the OSPF.